Hello, I'm Kevin with EMIT Technologies, and today we're going to cover some of the causes of catalyst failure and some of the things that would cause poor performance on a catalyst element. What causes the damage to a catalyst? Aging, loss of catalytic activity due to the loss of active surface area. So what that means is basically over time we've worn down the surface of the catalyst element. Okay? And it just basically wears down, rubs it down, particulate matter and debris, soot, all kind of rub on this and wear it down. And it removes part of the wash coat, and with that go active sites or precious metal sites. And just simply a life process of the catalyst element. This would be normal wear. Another cause would be fouling, loss of catalytic activity due to the deposits of carbon material. So what that means is you've basically gotten carbon, which is a conductor, to short out these sites so that these sites are no longer as good a conductor as they were before for the electrons. So all of these sites become shorted out, and the more sites you lose with carbon deposits, the poorer the performance of the catalyst, or the more carbon you have, the more the catalyst performance is impaired. Okay, other things that cause damage are masking or ash. Ash is a normal deposit coming from a natural gas engine, and the ash in the catalyst fills these cavities up. Okay, and there's people that try to wash it out and do whatever, but what happens is you kind of cement it in when you wash it. Your best policy when you fill it up with ash or you start to mask off these sites is to simply blow it out with air. Sintering, temperatures over 1250 degrees. Sintering is a high temperature that's too hot for the precious metals, where the precious metals will actually pool up. And then the other thing that happens is this alumina wash coat starts to deteriorate and get soft. And so now as it falls and it collapses around the precious metals, you lose sites. You basically have smothered the precious metals, so they're no longer able to make contact with the exhaust gases that you're trying to change. Okay, poisons, H2S, phosphorus, sulfur, magnesium, calcium, sodium, heavy metals, anti-Cs, and glycol or antifreeze, and galvanized flex pipe, any galvanized pipe, greater than 0.05% in the exhaust stream will tend to poison the catalyst element. Okay, and so what a poison does is it attaches itself to the precious metal itself. It's much like a carbon deposit shorting out at the active site of the precious metal. So as more and more poison embeds itself in the catalyst or is developing or deposits itself on the catalyst element, the more of these sites that become inactive, and the performance of the catalyst starts to wane or deteriorate. Okay. Extended periods of being wet. When you have a catalyst, say in the back of a service truck or sitting outside, and it gets rained on, it gets water, it gets snow, whatever the reason may be, it's not a good situation for the catalyst, because this substrate or this foil is ferritic stainless steel. It can actually rust, and what happens is it delaminates the wash coat as the rust starts to build up and pushes the wash coat off the foil. No different than the rust on paint on your car. It pushes it away, and the catalyst is damaged at that point in time. Other things that will cause that are H2S is not only a poison, but the moisture in the exhaust with H2S will deteriorate that foil very rapidly. Catalyst performance, there's a few things that you can do. When you and I are trying to adjust an engine or tune it or adjust it for emissions, some of the main things we have to look out for that we have control of are the air-fuel mixture, that's number one, the correct temperature. If the temperatures are too low or too high, Too low, the catalyst won't perform the way it should. Too high, you'll damage the catalyst. For carbon monoxide, the temperature is around 450 degrees where it reaches its maximum. And for NOx, it's typically between 750 and 800 when it reaches its maximum, 850 degrees for sure. And then your other hydrocarbons that you have, or VOCs, it depends upon what that constituent is as to what temperature it takes to break that carbon chain down or break the pollutant down. And then the last thing is, and probably the number one thing that we see out there, is no exhaust leaks that allow free oxygen in the exhaust stream. And this would be strictly for the NSCR catalyst operation. For an oxidation catalyst, we're not worried about the catalyst element itself, or the oxygen, excuse me. For NSCR operation, we need to make sure that we maintain the oxygen content in the exhaust stream at 0.5% or less. And that maintains the free oxygen at a low enough level that the carbon monoxide and the remaining VOCs can utilize that oxygen and then go after the oxygen that's attached to the NOx. Things that cause pretty serious failures on catalyst or catalyst performance are leaks. Things like these bellows being blown out right here or cracked, that'll allow air into the exhaust stream. And when you allow that air into the exhaust stream, the catalyst sees that free oxygen. You reduce your carbon monoxide and your VOCs at a better rate, but your NOx performance will be greatly impaired. Commonly, if you see ash on the outside of the exhaust, you know that there's a leak somewhere close by. You can see this crack travels all the way along in here. And when you start that engine up, that ash is washed out from the moisture from startup, and then it builds up on the outside of the pipe. It's an easy sign to spot a leak. Okay, this unit obviously had a big backfire. It stretched and deformed the bellows out. Probably the deformation on the bellows itself wouldn't be a problem, but what we worry about is this particular one with this band clamp. This would be a Waukesha 7044 or 7042. With this bellows, there's a flange down here on the bottom, and we'll see those get deformed when you see a backfire of this magnitude up here. And they'll suck air in and cause a lot of grief for you. Here's another example of just plain, there's ash showing on the outside of the housing. You can spot that from the ground, and there's a crack right here. Just gotta weld that up. That's ahead of the catalyst element, and that'll cause the catalyst poor performance, or cause poor performance on the catalyst. Here's a classic. Bellows broke off and somebody welded them partially, but again, right here you're seeing opportunity for oxygen to be drawn into the exhaust stream. Wastegates. Anytime you have a wastegate dump like this, as this again is on a Waukesha, you'll see the same thing on Caterpillar engines or any other engine manufacturer. This is supposed to swell up and seal as the engine gets warmed up. As this collar in here, the spool gets warmed up, it's supposed to seal in this surface right here. If that does not seal when the wastegate is dumping, it will pull oxygen into the exhaust stream and cause poor catalyst performance on NOx reduction. Another thing that happens is that goes across the O2 sensor in this situation. The O2 sensor sees that oxygen and starts to richen the engine up. And in that case, you could easily overtemp the catalyst element. Okay. Here's a common place. You've got a gasket that's missing down here. It's been blown out. And in this particular one, this stud was broke off. And this, you could pick that nut up out of the hole. It's never fun to repair these, but it's critical that these are repaired for the performance of the catalyst. A leak like this would cause a failure as far as emissions reduction across the catalyst. Here's showing missing gasket is what this one is showing. You can see where the exhaust gases were racing out right here, or on the other hand, they can be drawing air in at the same time. Same with these marks right here. You can see there was no gasket there, and that housing was leaking. This particular unit, they couldn't even get close to meeting emissions. Okay, here's the housing that was on. You can see where it was drawing the exhaust gases out, or the exhaust gases were leaking out, and the oxygen was drawing in. Same catalyst housing here. You can spot those identifiers that you have a leak. Okay, this would be a CAT 3300 series flange with a Caterpillar bellows on it. And this flange is free to turn on this bellows. And if you use an ANSI flange gasket on here, that gasket is clear out here, and it doesn't seal against that flange on the other side. You have to use a Caterpillar gasket on Caterpillar flanges. Just a note. Okay, galvanized flex pipe, that is a definite no. The galvanized poisons the catalyst, and then these leak real bad after a short period of time. They'll draw air in through all of these joints. The other bad thing about this picture is the oxygen sensor is located above the bellows. Sometimes you can't avoid it, but in most situations you always want to have this oxygen sensor located down here in this portion of the exhaust ahead of the bellows. That way if you develop a leak in the bellows, or in this case the flex pipe, you don't see that oxygen on the catalyst element and you don't overfuel the engine. This particular catalyst failure was caused from a generator. This was a 3406 Caterpillar. It was at the Cat dealer, and they were starting the units. They were gen sets. They were starting the units with no load, and they turned the air fuel ratio controllers off and running the units on propane. And when they're running that unit, not only was the engine not loaded, so you had poor combustion performance and low cylinder pressures, therefore low cylinder temperatures, you were running on propane for a test run when the unit was set up for natural gas. So extremely high amounts of unburned hydrocarbons making it to the catalyst foil and actually combusting and burning on the catalyst foil itself. It's a pretty common thing to see. This is an extremely high BTU failure. Okay, here's another one, similar type of failure. This one is excessive heat from unburned fuel. In this case, the fuel was on a commingled well. It was on a 3408 Caterpillar and on a screw compressor. And what was happening is they were actually carrying crude oil up into their fuel gas. Their coalescer wasn't working well, and that crude oil was actually burning in the engine in small amounts, but it doesn't take a lot to really disturb the system. Here's a catalyst. I actually damaged this catalyst myself. This was on an 817 Waukesha, and customer had built their own exhaust piping. The unit had failed in its emissions test. I went out there to take a look at it, and brand new catalyst element. I took their catalyst element out they had in it that only had an hour or two of runtime on it, and I put this catalyst element in, and it was passing fine for a few minutes, and then the numbers began to deteriorate. And it was a difficult situation to find, but what we ended up finding was the exhaust piping was too small on that unit that was supposed to have 5-inch exhaust piping, and they went down to the local exhaust shop and got some 3-inch for a diesel truck. And so what that back pressure did is made the engine not breathe correctly. Therefore, the cylinders were not purging, and that raw fuel was going out into the exhaust. Now this one, you can tell by the surface that the exhaust gases were not hot. They were not hot. They didn't have a big load on this. But the raw fuel was coming in here and burning. And you can see that it starts to react to the precious metals right in here. Okay? And when it reacts to those precious metals, it starts to oxidize, basically burn. And because the temperature was low, the surface was protected. Looking at this catalyst on each side, it was less than an hour old, and I had put the catalyst in, and still it had failed in a short amount of time. And it's just due to a poor running engine or a poor breathing engine, and all the unburned hydrocarbons building up, oxidizing, and had we continued to let this run, this would continue to burn out and get deeper and deeper. But this side of the catalyst would remain just fine because of the low temperatures keeping it cool. So the other thing that this really shows us really well is what part of the catalyst is doing the work. When you're looking at a NSCR catalyst or a catalyst for a rich burn or a three-way catalyst, the activity takes place shortly after it enters the catalyst foil. And as soon as it depletes the oxygen, that activity stops. Okay? And then the exhaust gases just continue on through the catalyst element. So the flow path was this direction. Okay? So one thing we know by doing this is that we've depleted all the oxygen, and it becomes a laminar flow, or it goes through like a shotgun. It no longer is tumbling, and you've depleted the oxygen that's in the foil and also in the exhaust stream that can react, that's making contact with the sites, precious metal. So we know that in an NSCR catalyst, the activity is on the leading edge. So this tells us a couple of things. It tells us some maintenance items as well. So the maintenance items that it tells us is only one side of this catalyst is getting used on a rich burn engine. If we want to do maintenance on this catalyst, we can blow it out with air and turn it around so the exhaust gases are coming in on this side where you still have foil that's in great condition. Now this unit was no longer usable because it had melted so much that it started plugging it off. The back pressure is what we really saw increase. The numbers were failing fast, but the back pressure was also increasing because we were literally melting the foil and it was sealing itself off. Okay. This is a catalyst that came out of a 7044 Waukesha. And this is what happens to a catalyst element. Maybe you weren't running at 1250 degrees, but you were very, very close to it for extended periods of time. Now, on this one, the panel that they had on the unit was not reading the exhaust temperatures correctly. The exhaust temperatures were actually about 250 degrees hotter than what their panel was showing, and therefore it was not going down on shutdowns. And the engine was running rich as well. It's kind of a common practice on Waukeshas to run a little richer than most engines. So this is what extended periods of high heat do. You won't damage a catalyst right away at 1250 degrees, but it doesn't take long, and several cycles this foil expands and contracts, and you can see this one kept contracting further and further until there were cracks in it. Okay. I always want to look for the obvious on catalyst failures or when things aren't going right. The obvious on this picture is the white tells you that this has been very hot. We use a high temperature coating on the catalyst housings. You can see the door did not change color, but the housing itself changed color. And look down the line, you can see this one and you can see this one were also white. These were all in the same location, and what was happening is they were having cylinder head failures on their units. And again, this is the same location that this element was on. This is the same housing that came out of. And the temperatures were not showing high on their panel, but so they were not shutting the units down. They had no record of overtemp, even though these housings had been turned white. In order for these housings to get that white, they literally have to be red hot. Okay, so this slide is a slide that just shows that white housing up here again. Just the obvious. You see where this one isn't white. The temperatures haven't been elevated too high, but this is pretty obvious. Just again, your best troubleshooting is look for the obvious. More times than not, the obvious are are what take care of it. The really hard to troubleshoot units are pretty few and far between. Okay, here's a location. Here's another issue. If you are used to Waukesha, this one happens to be a 7044. The exhaust temperatures are normally very hot. This one is a little hotter than normal. This was inside a building, that's why the red housing shows up so easy. But also we're showing that it's got that insulated pipe on it as well. On this particular unit, the insulated pipe had joints in it and had leaks under the joints. We were seeing catalyst temperatures meeting right at 1250 on the inlet of the catalyst and about 1300 out. And their only issue was the engine was continuing to richen up as they tried to make it meet emissions because of the exhaust leaks in the joints that were underneath this insulation. When we tore the insulation off, we could see the leaks in the pipe. It's not uncommon though for a Waukesha to run this hot. This one has remote mounted O2 sensors. This transition manifold right here is where Waukesha puts an 18 millimeter port. This is not a good spot for an O2 sensor. They don't survive. So what we've done is moved this O2 sensor around to the back side and then brought the return off of that line here. And it's a remote mounted O2 sensor, and we'll talk about them more later. Okay, here's the remote mounted sensors right here. Okay, this is another catalyst element. They were getting a buildup on the face of the catalyst element. And what was happening here is the tetraglass, the gasket around the catalyst element from the catalyst ahead of this, the first pass was deteriorating and it was building up on the second pass. This was also the same units. You see these cracks after we cleaned it up. This is the same unit that they were running real high temperatures on, and temperatures higher than the tetraglass was able to withstand. Again, their panels were not showing the correct temperature, so therefore they continued to run. Here's another unit. This was a 399 Caterpillar. Unit was not meeting emissions. Customer called us out and said they had put new catalyst elements in it. Well, they put new catalyst elements in it right next to this one, and so this one was very plugged. Obviously, that's just simply ash, and you can most of the time salvage these catalysts if they haven't been over temped or they don't have a ton of years on them. You can just take them and blow them out with air and blow that ash back off of there, and then flip them around so the inlet is the opposite side of the buildup. And a lot of times you'll meet emissions just fine with that same catalyst. Okay, anti-seize is another thing that poisons the catalyst. You always want to use a moly graphite based unit. H2S, it will definitely rust. Moisture is or water is a normal product of combustion across the catalyst and in a natural gas engine combustion process. And when you mix that with H2S, it's not a good thing. It would cause rusting very fast. This catalyst element was not very old at all. This was in a 3600 series Caterpillar, and this unit was less than a year old. So this is the effects of H2S. Okay. Just to show the amount of water that's produced in a catalyst when you start it, we'll take a look at this video. Okay, and it's just amazing how much water is produced, but it's dried off right away. Don't leave those catalysts wet for long periods of time. Don't leave them in the back of a pickup or sitting outside on the ground. It will damage the catalyst. A new or rebuilt engine has to run at rated load for at least 50 hours with a catalyst without a catalyst in the housing. Without is the key word there. In the catalyst housing, recommended engine oil parameters: consumption less than 0.0015 pounds per brake horsepower hour. Phosphorus at 0.09% by weight, zinc 0.04% by weight, and ash less than 0.5% by weight. So that's recommended engine oil to use with a catalyst. Another thing you want to be careful of or be aware of is certain engines, they recycle their crankcase gases. And on this particular one, the exhaust gases are recycled and put in the air cleaner on this side. This much oil, this much blow-by is very hard on an engine to push back into the engine, and it causes those cylinders to run differently than the cylinders on the other bank. So this is a cross-flow after cooler on this one. So the exhaust gases were coming in on this air cleaner and then coming around and going to the feeding the right bank, even though they're going into the left air cleaner. This engine was found to have two bad cylinders in it. They're still running, they were just passing oil very bad. Okay, this stuff looks like pea gravel. You may have seen it before. Looks like small rocks or material that's building up. Looks like somebody might have left it out on the ground, and before they put it on the unit they had got rocks or gravel in it. This particular one was actually sodium from a commingled well. And that sodium, as it passes through the engine, turns into a solid as it goes into the exhaust, reaches a given temperature and turns into a solid. Here's more of the same. Looks like rust or gravel or dirt in there. And this was sodium that caused this. Okay, one of the things we want to have is some of the features that are on there is we have to have a way to measure the back pressure. You can do this manually by a drop tube ahead or behind the catalyst, or you can use a pressure transducer to measure the differential across the catalyst element. In this situation, here's a model of the way we'd like to see the tubing on. This is kind of extreme, but it gets the point across that you always want the moisture running away from the pressure transducer if you're going to do that. What do you do with the old dirty catalyst? Well, there's a couple of things. Mainly blow them out with air and keep trying to use them. If they're no longer performing at 100% on their own, and they need some help, you can add them in as a secondary catalyst element. You can put them in the front slot as a shield for your new catalyst element. You don't throw them away. They're valuable for recycling. We give you credit towards the new catalyst element. Turn in your old one, acquire your old catalyst elements, and when you get to a given amount, we will recycle them by the pound. Cleaning catalysts in the field, your best bet is to blow them out with air. It works more times than not. The things it won't work on are obviously oil, it won't work on carbon, and it won't work on antifreeze. If you got a green hue to your catalyst and you've lost a cylinder or you lost a turbo and you pushed a bunch of antifreeze into the exhaust, you always want to make sure that you run that engine a while before you put a new catalyst element in. If you have a bunch of antifreeze and things that need to burn out of the exhaust after an engine failure, make sure you run it for a while before you put the new catalyst element in. Now we're going to cover catalyst housings. There's several different catalyst housings. There's stainless steel construction, which is heat and corrosion resistant. Carbon steel is very popular because of the cost. It's less expensive and easier for construction. Stainless steel has twice the expansion and contraction characteristics of carbon steel. Therefore, it cracks a little easier. It'll expand farther and shrink further. If you're going to get a crack, you're going to get one in a stainless steel housing long before you ever get one in a carbon steel housing. Silencer catalyst combinations, you can get the catalyst housing and the silencer housing all in one unit. There's round or there's rectangular elements, and there's units that have containment rings, that's in a round housing, and there's diffuser plates in the round housing as well. Here's a picture, a model of a housing. Here's a common housing, it's called an EAS. This housing would be EMIT accessible with a silencer is what EAS stands for. Okay, here's a full stainless steel housing. This is going to last a long time. This particular unit happened to be on a diesel engine. EZ housing, this is a replacement housing for small horsepower natural aspirated engines that don't carry a heavy load. You can mount this right down by the exhaust manifold and get as much heat utilization as you possibly can from the engine. Typically only applicable in low horsepower situations. Low heat is the main thing. You're going to utilize the heat coming off the engine as close as possible. Probably wouldn't want to run this on a fully loaded engine. The temperatures might be a little too hot for something this close to the engine. Here's another look at another EZ housing. Okay, EA housings, they're usually round, not usually, they are round, and they have a catalyst element in them or a slot for two elements, and there's no silencing characteristic to this at all other than from the diffuser plate and the catalyst element itself. EAS catalyst housings and standard grade silencing. This is just a silencer. They're usually the same dimension all the way from one end to the other, and you have your access door, and there's no other access, few test ports, and that's it. EAH catalyst housings, they're catalyst housing and hospital grade housing silencing together. So you have your catalyst housing on this end, and then the silencer is here. You can see the silencer is quite a bit bigger than the catalyst housing. Okay, the assembly of it is you got your catalyst elements that go in the slot. There's a gasket material called tetraglass, comes in a roll, and it's got an adhesive back on it. You just stick it to the catalyst element and drop it in the spot. And this gasket material right here, also 1.5 inches wide, it just comes in a roll, and you cut it to length and you stick it inside the door and on the contact surfaces where you want your seal. T-bolts, we use these on our EA housings. Fast and easy way to take the door off. They're a 3/4 inch wrench will take them off. That's a 1/2 inch bolt. The other nifty thing about this is this 1/2 inch bolt also fits in the catalyst lifting eye, and so you can use the same bolt to lift the catalyst element out. Data tags on the EA housings, they're usually on the inlet end. Single or dual pass, you can run them less than 500 horsepower. Typically that's what we use the EA for. Again, is less than 500 horsepower. Not a standard, not a hard fast rule, but it's pretty common. So this particular unit has 2 elements in it, and here's the flow path, and goes through the silencing and the silencing tubes and out the tailpipe. EA housing also has these containment rings. These were mostly in effect for the earlier housings, the earlier catalyst elements, before they were a brazed rigid substrate. This kept the catalyst foil together in the event of backfires, and just all around supported the catalyst element. This diffuser plate, this is on the inlet end of an EA housing. It's a 50% open area, and it's just that, it's a diffuser plate. It keeps the exhaust gases from passing through only the center of the catalyst element. It will spread it out over the full face of the catalyst element. That's what it looks like up close. The slots in a catalyst in an EA housing makes no difference which slot you put your element in. If you're only going to put one element in, some of the things that we think about are if the catalyst does have a catastrophic failure, we usually like to put it in the front slot right here. And the reason being, when you have a catastrophic failure or an over temperature on a catalyst, it's hard to get that catalyst element out, and you'll want to be able to get to the back side of it and get your pry bar in there and start removing the catalyst element. Here's a common EAH housing, so it's a EMIT accessible. It has a spot for 2 elements, and it's got a hospital grade silencing on it. 3306 package. Pretty common use of a housing. This particular picture, the bellows are pretty long. We don't typically like to have bellows that long. Bellows that long will tend to break and crack prematurely. EL housings, so that's emit linear flow, and so the exhaust gases come in this housing, and what they do is they come through and they go through the elements, and then they come out this way, and they go out each direction, but the inlet is between the elements, between those doors, and there's a bulkhead across the end of here to prevent the gases from going straight through the housing. And here's the exhaust flow path on an EL housing. So the gases come down the middle. Get my pointer working here. Gases come down the middle, and then they go through the catalyst elements and out through the silencing tubes and chambers of the silencing housing. You see the bulkhead here on this end. And on these particular housings, you don't necessarily have to run all the elements that there's slots for. You could put blanks in these units up here and only run elements in one side. Until you needed further emissions reduction, then you can add more elements. But in this situation, you're going to have to run blanks or elements. One or the other has to be in these slots. Here's an EL housing as well, but it only has a single door and has room for 1 row of elements. You can get these with from 2 to 4 elements in the track. But again, any place you don't have to have any place that you do not have an element, you have to run a blank. Okay, this is an EB series, EMIT base mount. They're mounted on the base. They stand vertical. Your catalyst elements go in the doors, stand here. This one will hold up to 6 elements. Again, the exhaust gases come down the middle and go from there. This particular housing shows 6. We build housings that hold up to 8 elements. Good thing about these elements is their ground level access. You can take the doors off. You don't have to get up in the air. You don't have to get a man lift or up on a catwalk to get these elements out. You're standing right at ground level. Okay, the exhaust flow path on these, it comes in the side, goes down the middle, and just like an EL, it's between the catalyst elements, and then go out each side. This would be a typical EB housing on a 3600 series Caterpillar. This one has insulation on the base of it, and the doors are over here. Here's a trunnion mount housing. These were mounted up. These were 3616s, I believe. And so the housings were quite a ways in the air. And the reason they're called trunnion mounts is they have a trunnion up here on the top, and they're free to move. What that does is allow this pipe to expand and contract, and this can swing back and forth. EL double door on a stainless. Again, the exhaust gases come in, go through the middle, and out through each side. You have test ports on the catalyst housings, and if you have a housing with 2 doors on it like this, it's going to be an EL housing. So the center set of test ports or thermocouple ports are always the pre-catalyst, and the ones outside the doors are going to be the post-catalyst. If you have a single door, you're going to be pre on the top and post on the bottom. That's if the inlet is to your left. There are some that are tipped over the other way, so you always want to look at the data tag right here, and it's going to tell you the flow path. Okay, this data tag on a single door will be on the downstream side of the catalyst element. Again, the flow path through a single door EL. And this is what the hardware looks like. You have the door. You have a channel cap, is what we call this piece right here. So this goes down, it's bolted on each end. And then you use a forcing screw to force it over against this bulkhead and seal it off. And then you finish tightening the bolts down once it's secured. Again, on a rich burn engine, it's absolutely critical to have these gaskets in place. I've seen where people don't put the gaskets in, and that allows the free oxygen to build up in the exhaust stream and causes the catalyst not to perform well. There's what it looks like when it's assembled. Here's a picture of the channel cap. Again, we've got a bolt in each end, and this forcing screw pushes on one bulkhead and it seals on this side where the gasket is. This gasket is the same gasket that we wrap around the catalyst elements. Again, it comes in a roll and it's got an adhesive back on it. You cut it to fit. ER housings. The ER housing, it's a dual pass, and typically for a rich burn, although it could be used on a lean burn, but back pressure is usually your constraint to keep you from doing that. The gases pass through both sets of elements, so they come in on this side, go through the catalyst elements, and then pass through. These are great for achieving very low reduction numbers, or excuse me, high reduction, very low emissions numbers. Incredible performance on these units. Again, very important to have the gaskets in place and sealing correctly, and to have these forcing screws pushing these two plates apart and sealing on opposite bulkheads. Okay, so this is what a real one looks like out in the field. You can see the gasket down each side. You don't worry about too much about it passing on the top from the first pass, because you got to go through the second pass anyway. There's no way out of this chamber without going through the second pass. Again, extremely low numbers. Tight regulations. ER housings, anything typically over or greater than 500 horsepower in a rich burn application, we would choose to put on the ER housing, just so that you always have the option to get those numbers very low. And here's the flow path. Goes through the top and down through each set of elements, through the silencer and out. Here's what the end looks like with the end cap off of the housing. You can see the exhaust gases are going to come in and go to one side, the left side, and then go through two sets of elements. Get great reduction, great performance. What the gaskets will look like as you're taking it apart. You can see this little bit of failure here, but these have been in there a couple thousand hours. These are in great shape, not an issue at all. This is something you do want to look out for, though. When you're dropping catalyst elements in, make sure you get all the old gasket material out or debris out of the channels, because that catalyst element is going to go down and sit, and if it doesn't seal tight, you're not going to get great numbers. You're going to get some gases bypassing the element. Data tags and then the flow path. Again, if you ever have questions where your pre and post is on it, you can look at the data tag and look at the flow path tag. It'll tell you which way your pre and post catalyst elements are. These charts are available. What this is telling us is the capacity. If we had a 4 capacity housing, and if we put only one element in, this is the inlet, this is our arrow showing us the inlet. we're going to have one catalyst and one blank. This is for an ER housing. Okay. If we're going to run two elements, we're going to put those both on the top on the pre-pass, or you can run two blanks and you can put one catalyst ahead of the other and get very low numbers. Tend to increase the back pressure with a single pass on catalyst. Depends upon the engine. If you're going to put in three, you'd put two on the top and one on the bottom and put your blank in place. Always have to have those blanks wherever you're not using a catalyst. In a 4 position, again, you'd run 4 catalyst elements and you wouldn't need any blanks. And so on and so on. And this chart will go through and show you that all the way through. Okay. Absorptive silencing, we usually put an X in the notation on the catalyst housing. So if you had an EBX, that would be a EMIT base mount with an X, and that has ceramic wool wrapped on the inside of the housing. Very, very quiet. Very, very great performance and sound attenuation reduction. Okay, so here's a model of it. So you got your outer shell, you got the ceramic wool, and then you've got perf plate lining that to hold the ceramic wool in place. Okay, there's what a cutaway view would look like. Here's a reactive silencer. There's no absorptive blanket in it at all. You're only using the dimensions on the silencing, or the dimensions on the housing of the silencer is sized according to the sound that's being produced by the units, the waveform. So these are modeled and engineered to reduce those sound waves only by percussion. There's a typical look at one of those. So to recap, one of the things we need to have this catalyst, one of the things we need to have for a catalyst to perform correctly, you got to have temperatures right. CO reduction reaches a maximum at 450 degrees Fahrenheit. NOx reduction reaches a maximum at 750 degrees Fahrenheit. Maximum temperature is 1250, so optimally you're going to be more than 750 and less than 1250. You're seeing a 25 to 100 degree rise across the element. That's great. You start getting over 150, you know you have issues going on. For a 3-way rich burn, same thing. Catalyst has to be sized correctly. Temperature has to be 750 to 800 degrees. Temperature not above 1250. Oxygen content not above 0.5% oxygen. Catalyst installed properly, not to allow untreated exhaust gases to bypass around the element. Catalyst element needs to be clean. For a lean burn, very similar, has to be sized correctly. Temperature at least 450. Temperature not above 1250. Catalyst installed properly, not to allow untreated exhaust gases to bypass around the element. Catalyst element clean. Low temperatures can also be a problem. Some of the low temperature causes are catalyst installed too far from the engine. If you're in the northern states and you have cool air, wintertime, cool rain, snow, and you're trying to do an emissions test and that housing is outside and you've got a lot of distance between the engine and the housing, it's entirely possible that you're not going to be able to reach the temperatures needed for the optimum performance of the catalyst. Silencer installed ahead of the catalyst. We've seen them installed backwards, and the silencer takes a lot of heat out of the exhaust. They'll function, if the heat's up there, they'll function the same. But the reality is we like to see that silencer after the catalyst. Ambient temperature cooling the exhaust, like I said, rain, cool air, ambient air outside, wintertime. It can be challenging sometimes to get lean burn temperatures up to get a catalyst to light off correctly. Just a little demonstration of what can happen when you just blow a catalyst element out. 94% reduction. You know, if you're at a 1 gram permit, you're going to be right on the cusp of not meeting. So if you went in at 5,500 ppm pre-catalyst, you'd be coming out at 330 post-catalyst. And 2500 pre on NOx, you'd be coming out about 150 ppm post at 94% reduction. Take that catalyst out, blow it out, and flip it around, and you could get a 96% reduction. You dropped 110 ppm on your post CO numbers. And on your NOx, you dropped another 100 ppm there just by blowing the units out, or excuse me, 50 ppm here, just by blowing the units out. And so if we went through the percentages and we got back to a 98% reduction, we cut those numbers by 1/3 just by blowing the catalyst out. Always good maintenance to keep the elements blown out and clean. 99% reduction, that's closer to a new catalyst element on everything's brand new, engine's running perfect. 5500 in would be 55 ppm coming out. So we're 1/6 of where we need to be for 1 gram permits here. So it's a great reduction, great opportunity. This will conclude today's session. Thanks for watching. I hope we provided you some value today, and we'll catch you next time. Thanks and have a great day.